So speaking of spatial scale and other map conventions, that's what we're going to talk about today. Map conventions are the accepted rules or norms of map making. They help us manage our expectations and organize maps. And so when we align our maps with conventions that our audience is used to seeing or used to obeying, that's when we have a really effective map product. So one example we've already talked about is that north is usually up on maps. We will talk quite a bit about scale today. And then we'll get into in the next few lectures dealing with projections and coordinate systems. So raise your hand if this map is really familiar to you. Is this the one you saw hanging in your classrooms? For some people, maybe yes. I'm seeing a few hands raised. But what are some things about this map that maybe are not conventional or not what you're used to seeing? Anyone want to offer some observations? Yes. Yeah, as we'll discuss, I mean, the majority of humans on Earth do live in the northern latitudes. You know, there's quite a few people live in the southern latitudes as well, but a lot of the maps we're used to seeing, especially years ago, when people thought a little bit less about this, are more focused on the northern latitudes. What this map projection does is it actually enlarges areas around the equator, as was correctly pointed out, to try to achieve an equal area distribution on the map. So what it's trying to do is actually have a one-to-one comparison of the areas of continents that happen to fall close to the north or south poles and the areas of continents that are near the equator. So it has the effect of making the Sahara Desert look really big, which in fact it is really big. Especially when you think of it compared to Europe. It looks like you could fit 2 or more Europes within the Sahara Desert. Kind of striking to see. What about the shapes of features, especially as you get further north or south? What's going on with that? Yeah. Yeah, so things are getting a little bit smushed, a little distorted, or maybe our conventional way of seeing those continents is actually a little distorted, and we're used to that. Turns out all maps are distorted in one shape or form. There is really no way to get a two-dimensional map that represents a three-dimensional globe without that distortion process. So the trade-offs you make when you're making a map affect how that distortion occurs, and you might favor some things over others. As I mentioned, this is an equal area map. It means that, you know, Iceland here is going to have an accurate area distribution. Like if we had a map scale here, we actually traced the outline of Iceland and calculated the area, it would be an accurate comparison between Iceland and, let's say, you know, islands down here in Southeast Asia and Japan. Whereas other maps, which are designed more for navigation, you might have a regular grid spacing. You see these lines of latitude and longitude here kind of distributed at different intervals, depending on where you are on the map. If there's a large gap between these lines of latitude, even though they have a constant increment, and that is to achieve that equal area projection. So this is, you know, one map that kind of illustrates how things can be a little, I mean, conventional in a way, right? We have north up on the map, but we're also breaking with what some people might be used to by showing this with an equal area distribution. So raise your hand if you've seen the show West Wing. Every year, this makes me feel older and older. This was like, so when I was in college, like someone down the hall had a box set of DVDs of the show. So we were all into this show before streaming was really a thing. So I'm feeling older and older by the year. But let's check this out. So I think maybe you agree that this clip from popular culture does a good job at illustrating how these map conventions can affect the way that we interpret the world around us. And nothing against the Mercator projection. It's still commonly used. Actually, a version of the, sorry, hold on a second. Go next. Just double check there are no crises here. Okay, good. So what I like about that clip is that it illustrates how conventions can have unintended consequences. And nothing against Mercator. Still, Mercator is used for like Google Earths, any sort of web mapping application. You're likely using a Mercator projection. But most people would not know those relative size relationships when they're looking at the map. And Mercator really designed that map to be a navigational tool for European sailors, right? He was a German cartographer at a time when Europeans were navigating the world's oceans, and that's what the map was designed for. It wasn't necessarily designed for teaching social studies to fifth graders in Montana in 2023, right? So it's important to understand how those changes in size relating to the fact that it is not an equal area projection can affect how readers actually do understand the world. So some schools have adopted different projections, like the Peters projection I was showing you earlier, because it does have a better representation of the relative size of places, which might, imply some importance. If we assume like a constant population density, larger features will have more people living there, and maybe we should pay more attention to them. So yeah, what are some other standard map conventions in addition to just projections? I said north is up, typically. Yeah. Yeah, so typically we split. I think I'm used to seeing the Atlantic Ocean as central and the Pacific being split on either side, right? But I get exactly what you're saying. So splitting up the oceans, or like, what is your focal point? We tend to have that Atlantic-centric view, so that Europe's on one side of the Atlantic, North America's on the other side, and the countries that are further away get kind of put at the far ends of the map. So where you focus your map projection is important. The colors you use, right? I mean, it makes intuitive sense to use blues for water and greens for land, etc. But that is a convention. It doesn't necessarily have to be that way. So yeah, lots of good things to think about. And the basics of creating a map with conventions are choosing your projection, choosing your map scale, and then choosing your symbology techniques as well. And you have control over all of that in a GIS. So in terms of map scale, maps can cover a huge range of scales. Here's an interesting map of the topography of Mars. Also showing one of the largest topographic features in our entire solar system. Olympus Mons right there, which is pretty cool. Different sort of projection here with curved lines of longitude. But we can see our scale bar here, 1 to 70 million. So today I want you to take home an understanding of what those fractional scales really mean. We also have maps that are very detailed, right? Here is a piece of Mars. This is a piece of a chondritic meteorite, which geochemically can be linked back to Mars, showing minerals that are there. But notice the scale bar here is only 1 millimeter for this bar. This is a type of scale we would call a graphic scale, because it is not a fraction, it is just a graphic. So map scale, if we were to define it, is the ratio of distance on the map to distance on the ground. Keyword there is ratio. You can represent it as a fraction. You can represent it as 1 to 100,000. That would be the exact same thing. So if I rewrote this as 1 colon 100,000, that would be the exact same thing as 1 divided by 100,000. can do easy conversions by setting up simple equations. So we'll get a little bit of practice with that. I can guarantee you on some exam, you'll be asked to do some unit conversions related to map scale. So for a 1 to 100,000 map, 1 centimeter on the printed map, assuming that the person printed it on the right size sheet of paper, is equivalent to 100,000 centimeters on the ground or in reality. Or you could measure 1 meter on your map, and that would convert to 100,000 meters, right? The units, as long as they're the same on the numerator and the denominator, or on both sides of that fractional scale, you can use any units you would like. You can also use inches, right? 1 inch is equal to 100,000 inches. Typically, when you see maps that are designed to be used with inches, you'll see scales like 1 to 12,000, 1 to 24,000, because those are numbers that are easily divided by 12 inches per foot. When you see maps that are designed to use the metric system, typically they'll use nice round numbers like 100,000, because we have, 1 centimeter is equal to, 100 centimeters is equal to a meter, etc. So there are 3 types of scales. Here's a typical US Geological Survey topographic map. And we've got our fractional scale here. So it can be called a fractional scale or a representative fraction scale, RF scale. We have a graphic scale bar. And we also have what's referred to as a verbal scale. So in this case, the verbal scale is actually referring to the interval between topographic contours, which if you've used topographic maps before to navigate, you know that it means the elevation change vertically between each individual line on this map, which represents elevation values. So for instance, if we went 5 contours up this ridge towards Flagstaff Mountain, we would go from an elevation of around 6,200, of 6,000 up to 6,400, because every contour, actually I misstated that, 6,200 to 6,400, because every contour is 40 feet, 5 contours is 200 feet. So 3 types of scale: RF scale, representative fraction scale up top here, graphic scale in the middle, and a verbal scale down at the bottom. Questions? So let's think about some advantages. The nice thing about an RF scale is that you can measure with any units on the map. Let's say you had a metric system ruler, and maybe you wanted to be really detailed and you wanted to use millimeters. You could do that, measure with millimeters on the map, and then you could say, let's say I had 10 millimeters on the map. That would be equal to 24,000 times 10. So just add 2 zeros on there, millimeters on the ground. So really easy to use unit conversions to calculate distances on the map precisely. The graphic scale bar is probably more familiar to most people. Very intuitive, right? You can just look at a distance on a map, like from this high point here, 6578 is to Flagstaff Mountain. Looks to be about, 2,500 feet on the ground. So you can just read distances directly off of that scale bar. One advantage of a scale bar is if you were to resize this map and print it on a different sheet of paper. Let's say it was meant to be printed on a poster, like a big poster, but you actually printed it out on an 8.5 by 11 sheet of letter paper. The graphic scale bar will resize and still work, but the fractional scale, if you print it on the wrong size sheet of paper, will no longer work, right? Because you've resized that map, so that scale is now inaccurate. So that is one advantage of the graphic scale bar. It can be resized along with the rest of the images on the map quite easily, whereas the RF scale is only relevant if you've actually printed it on the correct size sheet of paper. And then I'd say the verbal scale is useful mainly because it's very intuitive. You know, you could also write something like one inch is equal to 2,000 feet. You could have different units on either side, just kind of providing a little bit more information for someone who might not be used to those representative fraction scales. Another thing to keep track of on maps, if you are in the United States west of the Mississippi River, generally, west of St. Louis, essentially, there is something called the Public Land Survey System, shown with these red lines here. And these red lines were used to distribute land and survey land when people were moving to the west. Well, people of European descent were moving to the west, of course. And these boxes are 1 mile by 1 mile. So if we were looking at this map here and we saw that red line and that red line, that is a section of the Public Land Survey System, and it's 1 mile by 1 mile in dimension. Make sense? Any questions? So there is a cartographic, very precise cartographic language around scale I want you to be familiar with. And at first glance, it might be a little bit counterintuitive. And that's because a small map scale actually shows a very large Earth area. That's because we want to think about the numerical value of that representative fraction. So if we have a map that covers the entire US, that's actually a small scale map. A lot of people would intuitively think, oh, a large scale map shows a large area, but that's actually not the case. So for small scale maps, we're mapping large areas. We have less detail and things are going to be more generalized. We'll talk about what that term generalization means, but it just means that, you know, in general, it's general. Things on the map are less detailed because you're viewing a much larger area. And so we're kind of zooming out. The opposite of that, for a large scale map, something like 1 to 1,000, is going to show a small area with more detail, and the features on the map are going to be less generalized. You're going to see all the detail that's possible. So for example, this is kind of a small scale map, right? We're showing the entire state of Montana. This is probably a 1 to, I'm going to guess like 1 to 5 million scale. A map of campus would be more like a 1 to 2,000 scale. So if you think about 1 divided by 2,000, that's a higher numerical value than 1 divided by 5 million. So that's why we call it a larger scale, because numerically it is a larger number. All right, so let's go through a quick calculation. How many feet are represented by 2 inches on a 1 to 24,000 scale map? If you're familiar with USGS topographic maps, they are typically in 1 to 2,400 scale, 24,000 scale, sorry. All right, you guys get to see my manicure skills. All right, so what I asked you is, you know, what is the ground distance for a 1 to 24,000 scale map? So what I would start by doing is just writing out the fractional scale. And we measured 2 inches on the map. Equals, you know, what distance in reality or on the ground? So the way I like to do these calculations is just multiply both sides by 2 inches. So there's multiple ways of doing this, but I just keep it simple. I say 1 times 2 inches is equal to 24,000 times 2 inches. So we can simplify that. 2 inches is equal to 48,000 inches. And we've got our answer right there, right? 2 inches measured with your ruler on a map is equal to 48,000 inches. We might want to convert that to feet, of course. So we can just divide that by 12 because there's 12 inches in a foot. And that will work out to 4,000, correct? So 2 inches on our map is 4,000 feet on the ground. And for the people on Teams, probably can't see what I'm writing. I apologize. But there are some good examples of how to do this in your textbook. Questions on how to do that? Okay. The key thing is just the same units on either side, right? Because this is a unitless fraction. It means that you can have any units as long as you keep the units the same on both sides. So the only unit conversions I expect you to know in this class are these. Probably, pretty familiar to you. Spending time in Denver, Colorado, I was always, very familiar with the 5280 number, but that's how many feet are in 1 mile. So I could ask you something like, 2 inches on the map is equal to how many miles based on this fractional scale. Metric system is really easy, right? But for the imperial system, 1 mile is equal to 5280 feet and 12 inches in a foot. So let's use map scales to think about how precise the symbols on your map would be. So a 1 point line, if we actually measured 1 point, on our page, it's equivalent to about 0.001 feet. So if we divide our map scale by 1,000, that gives us the approximate precision of a 1 point line on a map. So for a small scale map, like 1 to 1 million, a 1 point line might have a thickness on the ground of 1,000 feet. Right, so that would mean that if you're surveying for a 1 to 1 million scale map, like to get an accurate line drawn on your map, you don't have to be very precise, right? You have to be plus or minus 500 feet. You have to be in a pretty good range. But if you're making a 5,000 scale map and you are out there in the field collecting data with a GPS receiver that's going to create a 1 point line on your map, you're going to have a precision of your GPS unit that is within 5 feet, plus or minus 2.5 feet. So we're talking survey grade equipment in that case. So based on your map scale, it really does control how precise you have to collect your data and what level of precision is implied by the data set itself. We used a 2 point line that would just basically double the thickness of those features on a map. Okay, so I mentioned this concept of generalization, and generalization is something we do in a GIS to make a data set more manageable. So if we're showing a really broad area, but we're using the most detailed geographic lines possible, you're going to end up with like really large file sizes, maps that are slow to load. Remember last time I was showing you that example of that decimetric point or dot density map of the election? Like my browser kept crashing because that data was so detailed it had a hard time dealing with it. One way we handle is that we generalize to an extent that is appropriate for the map scale that we intend for the layers to be used on. So for example, if we were mapping the coastline here, I believe this is near, I think this is in Massachusetts, I believe. It's in New England somewhere. Like if we were creating data to be used on a 1 to 25 million scale map, we do not have to be that precise at all, right? These can be very segmented lines. When we zoom way out, we're not even going to be able to tell the difference. But if we're making a 1 to 50,000 scale map, we want to have really good resolution of our coastline, as shown by these black lines here. So a couple terms: generalization is used to simplify map features based on the map scale. The idea is to make the maps easier to use, smaller file size, etc. And source scale is the scale at which the data are captured, or it's the scale at which the data are intended to be used. So the source scale for each of these three layers is specified right here with an RF scale. The source scale of this layer, highly generalized, is going to be 1 to 25 million. So a couple more examples, right? If we zoom way out on this US highways map with a source scale of 1 to 2 million, it's pretty good, right? We get a sense for where the highways are in the United States. They don't look really segmented. They look pretty accurate. But if we start zooming in, we're going to need more detail to this data set. So Montana major highways, we might need a source scale of about 1 to 100,000, which is a larger scale. And finally, if we want to map city streets in Bozeman, we're going to need GPS accuracy to within 5 meters at about 1 to 50,000 scale. And even better if we're getting more detail than that. If we're talking about actually surveying people's property lines, you're going to have to be very accurate, of course, right? Because we don't want to end up with any legal disputes. So let's compare 3 different layers when we zoom all the way into West Main Street, right about where it turns into Huffine. I believe this is 19th right here. So if we have GPS accuracy source scale about 1 to 5,000, it's going to plot right on top of the actual features based on the imagery. If we're using a layer with a source scale of 1 to 100,000, it's decent, but still kind of offset from where the real feature is. We also see that the lines are more segmented. And then finally, that major highways layer, 1 to 2 million, it's going to be pretty much nowhere close to the actual road, right? And each place where you see a change in the orientation of that line, that's where you have a point in that layer that's actually giving instructions to the software on how to plot the line. So to create a very smooth line like this, you need a lot of points, a lot of vertices, and so that's going to result in a higher file size as compared to something that's way more generalized like the US major highways layer. All right, so a couple rules to remember. Maps should be plotted at a scale no larger than the smallest scale data layer. So that means that if we are using US major highways with a source scale of 1 to 2 million, our map should be 1 to 2 million or smaller scale. So we cannot make a map at 1 to 100,000 scale using that layer. And the opposite is also true. Same idea with raster layers. I show this JPEG photograph because, you know, for surface layers like any sort of raster data set, which shows us maybe an elevation map, something like that. If you zoom way in on it, you start to get pixels, right? It starts to look really pixelated, and that is an indication you're looking at a scale that the image was not intended to be used at. Just like our cameras on our phones, the resolution is going to control the size of the pixels. So a higher resolution sensor or a higher resolution data set will have more detail. All right, let's do a little bit more practice here. Another example of one of these scale calculations. So the setup here is that I want to select a scale Like, let's say we know the dimensions of some features we want to map, and we want to choose the map scale that we're going to use in our GIS to create this map. So we have a 4,000-foot long road. The road is running north to south, and our page size is 8.5 by 11. So where this might matter to you is insert new layout in ArcGIS Pro, right? If you're choosing your page size and you're inserting a map frame, it's going to ask you what scale you want to make that map frame at. And this is where this calculation would come into play. So we've got 11 inches to work with north-south, 8.5 inches to work with east-west. How should we approach this problem? So I like to make a little sketch. And so let's say we're going to use the entire extent of the 11 inches just to make this simple. In reality, we might use 10 inches. Actually, let's make it 10 inches. The usable space here is 10 inches because we're going to have some margins. And we want to show a road, something like this, that is 4,000 feet long. So that means that 10 inches on our map needs to show 4,000 feet on the ground. We're going to assume that 4,000 foot measurement was a straight line distance from like here to there. So we can just set up that RF scale, right? 11 inches, sorry, 10 inches is equal to 4,000 feet. Now to make this into a proper RF scale, we just need to get the units to be the same units on both sides. So we just multiply 4,000 by 12. Can someone tell me what that number is? 48,000. If you ever become a teacher, you will notice one thing I've noticed, which is mental math is impossible when you're at a podium. So 48,000 inches, 10 inches. And then we could just make this, we could drop the units, cancel them out on either side. Drop a 0 as well. 1 to 4,800 is going to be our RF scale, which is the same thing as 1 over 4,800. I do that right? Cool. So that is how we would approach that problem. So I will take a picture of those calculations and I'll post them on D2L later. Actually, I'll put them in the Teams channel because that's just a lot easier for me. So if you're not on Teams yet, get on Teams to see my solutions. I want to skip that exercise. We'll do that next time. But let's do another ArcGIS Online fun trick. So last time I showed you a group layer that was actually set up to use different map scales based on how detailed the layers were. And I sent out a couple of links in the Teams channel lecture content this morning, if you want to refer to those. But I'm just going to pull up Map Viewer. And this really, I think, is a good example of how generalization can be used on your map. With dynamic maps in particular, you can't really control which scale a user can view the map at. So let's say we wanted to display some census data. We could start off by adding several layers. Let's choose from the Living Atlas. Let's choose US states. US states generalized boundaries. Now you know what that term generalized means. Unfortunately, I went to the description for this layer and it doesn't actually tell us how generalized it is. It doesn't really specify the source scale, but let's zoom way in on this thing and see if we can tell. Yeah, it's pretty generalized, right? It's not a very detailed layer, so we wouldn't necessarily want to view that states layer at a larger map scale. Let's also add US counties. These are also going to be generalized. So now we see that higher detail level. Zoom in again to that shore of Lake Superior, see what's going on. Looks like the boundaries, the coastlines are actually the same, but within the states, we see the county boundaries. And then finally, let's add census tracts. This is even more detailed, and we can see that their boundaries are more precise. And so this is going to be more like a higher intensity in terms of loading the data because these are much more detailed layers, less generalized. All right, so I've added all those layers. Next thing I want to do is group them. So if I click the 3-button menu next to any of the layers, I can click group. It's going to create a group layer. I can rename that. Let's just say census geographies. And then I can drag my other layers into that group layer as well. I'm going to put the most generalized layer, the states, on the bottom. The least generalized on the top. And now what I'm going to do is I'm going to set it up to only display the states when we're really zoomed out. Did you notice that, how the census tracts took a little while to load when I zoomed way out? Also, like some of them are so small that they're actually bleeding together on the map at this scale. So we don't necessarily want to view these layers at this scale. So let's first actually highlight the census tracts. And on the properties menu on the right side, you can scroll down and you can set the visible range. So let's start with world. It means that you're zoomed all the way out. And it actually gives you some examples of the fractional scales if you click the drop down. So our current map view is 1 to 18 million. Let's make these visible all the way down to maybe the country scale. And then our next step will be to go to the countries. Same menu, the properties menu, and let's drag that slider to turn on the visibility at the country scale. And let's turn it off at the state scale. And then finally, for our census tracts, we will have it turn on at the state scale and have it extend all the way down to the most detailed map scale possible. So now what's going to happen, now that we've set that up, is when we're zoomed far out, we see just the states. We zoom in a little bit more and the counties turn on. We can see the counties within the states. That looks pretty good. Zoom in a bit further. And the states should be turning off, but I don't think that took for whatever reason. Try that again, right? We zoom in. We've got 2 layers turning on. Zoom in further, the states turn off. We can just see counties. Zoom in further, the counties turn off and the census tracts turn on. So this is a nice way of, dealing with generalization, dealing with map scale, and also making sure that any web applications or maps that you create are not going to be overburdened by the really detailed layers that you might want to include that only show up when you zoom way in on the map. Any questions about that? All right. Thanks, everyone. Have a good time in lab this week and see you next week.